Hello everyone here. I'm grateful to attend Activity Conference as a speaker for the second time in a row. And this time I will talk about security of WebSocket APIs. I'll present you several interesting cases of vulnerabilities found in real web applications. And I really hope my talk will give you more insight on how to test the security of WebSocket APIs more efficiently. But before we dive into the topic of the talk, I'd like to shortly introduce myself. My name is Mikhail Egorov. I live in Moscow, and I do full-time bug hunting and security research. As a bug hunter, I mostly work with BugCrowd and HackerOne platforms. I present my researches and share new techniques I've discovered by speaking on conferences. You can find my past researches on Speaker Deck and SlideShare sites and recordings on YouTube as well. As I've mentioned, this activity is second one for me. A year ago, I presented a talk about Adobe Experience Manager hacking here. You're welcome to follow me on the Twitter. My Twitter handle is oangel. On this slide, I'd like to outline my favorite works related to WebSocket security done previously by other researchers. Here you can find links to presentations and blog posts related to WebSocket security in general, WebSocket fuzzing, and details of vulnerabilities related to implementing WebSocket communications. In the beginning of this talk, I'll discuss known things like cross-site WebSocket hijacking vulnerabilities, authentication and IDO vulnerabilities, but from a prism of my bug hunter's experience. I call them known because you can find quite a lot of material, blog posts and write-ups devoted to these things. And in the second part of the talk, I'll discuss issues that are new and are related to reverse proxying of WebSocket connections that allow request smuggling. I call them new because they have not been much discussed in the community and very often overlooked. You might be aware that I've prepared 2 online CTF challenges about WebSocket security, and these challenges are indeed based on those new issues. To be on the same page about WebSockets, I'll make a brief overview of WebSocket protocol and how it's used. WebSocket is a high-performance bidirectional protocol. Our protocol is stateful. It means that firstly connection is established between client and the server, and subsequent data is transferred back and forth between them. In contrary, for HTTP, we establish TCP connection, then establish TLS connection, and finally transfer data. And this happens for each communication between client and server. And it's quite ineffective compared to WebSocket, where we establish TCP and TLS connection only once at the handshake part. And after handshake, both client and server can initiate data transfer over WebSocket connection. For that very reason, developers tend to implement WebSocket APIs instead of REST APIs based on HTTP, where it's possible to do. WebSocket protocol supports SEC WebSocket protocol header in order to negotiate one of standardized subprotocols between client and server. Those subprotocols are using WebSocket as a transfer protocol. You can get the full list of registered subprotocols by following the link presented on the slide. For example, Web Application Messaging Protocol, or WAMP for short, allows to do publish, subscribe, and RPC over WebSocket connection. And amusingly, there is even a SOAP subprotocol driven by Microsoft. One more way to add functionality to WebSocket protocol is extensions. The protocol supports sec WebSocket extensions header for that purpose. Currently, there are only 2 extensions are registered. For instance, per message deflate extension adds compression functionality to the WebSocket protocol. WebSocket connection could be initiated from a browser. Major browsers currently support the protocol. Same origin policy mechanism is not applicable to WebSocket connection established from a browser. For such cases, origin-based security model is used. Also, protocol does not offer any authentication mechanisms. Developers should implement authentication on their own. And one more often forgotten and overlooked thing, client must do masking of data in protocol frames. Masking is necessary for protecting against cache poisoning and smuggling attacks. We will return to these things later when discussing vulnerabilities and attacks. WebSocket support is huge nowadays. As I've said, major browsers support the protocol. Various web servers and proxies understand WebSocket traffic. Major cloud providers on the level of load balancers allow to proxy WebSocket traffic to your servers in the cloud. On the level of API gateways, you can build WebSocket APIs. For example, in AWS, you can use API gateway to build WebSocket API that calls your Lambda function, for example, based on data passed over WebSocket connection. To initiate WebSocket connection, client sends HTTP request to WebSocket endpoint with the set of special headers. On the slide, you can see highlighted mandatory headers. This request is called upgrade request because client sends connection header with value upgrade. In upgrade header, value WebSocket is passed. In header sec WebSocket version, client passes protocol version. And most of the times, only version 13 is valid. Header sec WebSocket key contains base64 encoded random nonce. Origin header is not mandatory. It might be used with web browsers for security reasons. I'm not touching HTTP version 2, so WebSocket upgrade should be done using HTTP protocol of version 1.1. Server should respond with status code 101 to establish WebSocket connection, and sec WebSocket key sent by client must be acknowledged by the server. It's done by calculating SHA-1 hash of sec WebSocket key from client and some constant, and afterwards sending this value base64 encoded inside sec WebSocket accept header. If handshake was successful, data is transferred between client and server in the form of protocol frames using the same TCP connection or TLS connection that was used during handshake step. And different types of frames exist. Field opcode defines type of the frame. One more important field in the frame is masking key. Client must generate 32-bit long key and mask data in protocol frames by XORing data with masking key. Server or intermediary like proxy should verify that client indeed masks frames. This mechanism should protect against cache poisoning and smuggling attacks. Note that server does not mask data in frames. This is only client responsibility. And now we know enough to start exploring vulnerabilities and attacks. And we are proceeding with vulnerability called cross-site WebSocket hijacking. I should say it's quite widespread vulnerability in web applications that use WebSocket APIs. This one is the first thing you should test for. As I've said, same origin policy mechanism doesn't work for WebSocket connection established from a web browser. This means that you can freely read or write to a WebSocket connection cross-origin from any site. To protect you from this, WebSocket protocol offers so-called origin-based security model. It proceeds as follows. On server side, during handshake step, origin header in upgrade request is checked against list of origins that are allowed to establish WebSocket connection. Browser automatically puts origin header in the upgrade request, and there is no known ways to spoof origin header. If origin isn't allowed, server immediately terminates TCP connection. Cross-site WebSocket hijacking attacks work when a cookie mechanism is used to authenticate WebSocket upgrade requests, and header origin isn't checked properly on the server side. This includes both cases when origin isn't checked at all, so any origin is trusted, or origin is checked by checked poorly. I guess you've heard about coarse exploitation research by James Kettle from Portswigger. Albinovox is his Twitter handle. This research was presented several years ago and is about bypassing origin checks when cross-origin resource sharing mechanism is used by a web application. Since both CORS and WebSocket have origin-based security model, all CORS tricks are applicable to WebSocket communication as well. You can find all known CORS tricks by navigating to the following link presented on the slide. Here I presented an example on how to make null origin for WebSocket upgrade request. I took this trick from James' work presented on the previous slide. You simply use a data URI for iframe and put all WebSocket related JavaScript inside data URI, and that's it. It works perfectly in latest browsers. Recently, Portswigger released WebSocket Labs on Web Security Academy. You can play with cross-site WebSocket hijacking in the labs. Link is presented on the slide. I usually use following HTML page with attack template for cross-site WebSocket hijacking vulnerabilities. Firstly, it opens WebSocket connection, then you have onOpen and onMessage handlers. Inside onOpen handler, you can send something to the server over WebSocket connection, and inside onMessage handler, you receive data and show it on the page. Let's explore the attack flow. You see here is a challenge from Portswigger Web Academy for cross-site WebSocket hijacking vulnerability. And we have a web application with chat here. We can type in some messages. And we see that our chat works over WebSocket protocol. And if we are sending word ready to the server, it returns the whole chat history back to us. So here is our HTML page for that hijacking attack. We are sending a ready payload and prints out chat history on HTML page. And when a victim visits our crafted HTML page, we should see that chat history is leaked to the attacker. Let's switch to authentication related issues and insecure direct object reference vulnerabilities. As we know, WebSocket protocol does not offer any authentication mechanisms, and developers have to implement authentication on their own, and sometimes they forgot to implement authentication at all, or roll out broken implementations. I want to point out that it's rather secure to check authentication only during a handshake step, because WebSocket protocol is stateful. You don't need to include authentication tokens in each message client sends to the server. And common secure variants of authentication are using session cookies or some form of authentication tokens. Now let's look at two cases of broken authentication I observe in bug bounty programs quite often. The first case, when some ID or global unique ID is required during an upgrade request as an URL parameter or header. This ID or GUID represents user or tenant. If you know that value for another user, you can impersonate him for WebSocket API. And sometimes you can guess the ID or leak it somehow, for example, through minor insecure direct object reference bug somewhere in web application. Another case, when there is no authentication at all during handshake, but some ID or GUID is required when you send WebSocket API messages. As an example of such case, let's look at GraphQL subscriptions. Usually at pass/subscriptions, there is an authenticated WebSocket API where you can connect to and quite often retrieve sensitive data belonging to other people. The other things you can find are insecure direct object reference vulnerabilities. There is a strong authentication during handshake step, but API is designed in such way that in API messages you observe IDs or GUIDs. And manipulating with these IDs or GUIDs, you can get or modify data belonging to other people. And this is the same as IDO issues in REST API. Now let's explore issues with reverse proxying of WebSocket connections. If you remember, I've called them new at the beginning of the talk. These issues allow to smuggle HTTP requests through fake WebSocket connection and access internal stuff that is inaccessible otherwise. Let's start with observing how reverse proxying for WebSocket is working. In the ideal world, we have a backend that exposes some WebSocket API on pass/socket.io, and client accesses API through reverse proxy. For example, we use Nginx as the front end and the WebSocket proxy. When initiating the connection, a client sends upgrade request to reverse proxy for pass/socket.io, and reverse proxy discovers that incoming GET request is upgrade request by inspecting HTTP headers like connection upgrade or upgrade WebSocket. If everything is correct, it translates that upgrade request to the backend. Backend answers reverse proxy with HTTP response that has status code 101, switching protocol. Reverse proxy checks that status of response indeed is 101, and header sec WebSocket accept has the correct acknowledgement. If everything is valid, proxy translate request to the client. And what's important, doesn't close TLS connection from client to backend. Otherwise, if response from backend isn't correct, reverse proxy immediately terminates that connection. After client receives a response from backend and verifies its correctness, we have direct WebSocket connection from client to backend. Client or backend can now send WebSocket frames to each other over connection. Client masks data in frames and reverse proxy, and backend should verify that frames coming from client are indeed masked. If they are not masked, connection is immediately terminated. That's how it works in the real world. But in reality, reverse proxies might behave slightly different from described scenario. Let's look at some real examples. Assume we have backend with publicly exposed WebSocket API on pathsocket.io, and there is internal REST API used for administration that's private and is not exposed outside. Now we have client that communicates with backend via vulnerable reverse proxy. The purpose of malicious client is to access private API. On the first step, client sends upgrade request to reverse proxy with wrong version in sec WebSocket version HTTP header. Currently only version 13 is supported most of the time. And reverse proxy doesn't check version and passes request to backend thinking that it's a good upgrade request. But backend declines upgrade request because of wrong protocol version and sends HTTP response with status 426 back to the proxy. Proxy doesn't verify status code and other HTTP headers in the response and thinks that backend is ready for WebSocket connection. Reverse proxy translates a HTTP response to the client with status 426 and keeps TLS connection between client and backend in open state. So there is no real WebSocket connection, only TLS connection. But reverse proxy thinks that WebSocket connection was established. If client sends HTTP request to /internal path over that TLS connection, he can access private REST API. Awesome. Here, additionally, reverse proxy also doesn't check that client masks WebSocket frames. I've created first challenge accessible at URL presented on the slide and posted it online at the beginning of October. The challenge is based on this idea. The task is to access flag on localhost port 5000. Sadly, but seems nobody solved this challenge. Sorry, but currently I cannot disclose the name of WebSocket reverse proxy I used for this challenge. On backend, I used Flask with Flask Socket IO module for WebSocket support and Flask RESTful for building a REST API. Backend works on localhost port 5000. And only WebSocket API on pathsocket.io is exposed publicly. Here is the intended solution for the challenge. We open TCP port and send two HTTP requests in a row. The first one contains upgrade WebSocket header and sec WebSocket version header with wrong protocol version. The second GET request retrieves the flag. That's it. Let's look in action that it's really working and I'm not kidding you. Here is our solution script. And we see it has two requests. The first one establishes fake WebSocket connection. And the second one retrieves the flag. Here is the host name with the challenge. And when we launch it, we get back the flag. In Soviet Russia, vodka drinks you written in lead speak. Varnish of latest version and envoy proxy of version 1.8.0 and below are vulnerable. There are also some vulnerable reverse proxies which I can't name currently. Good news that Nginx HA proxy traffic are not affected by this thing. Varnish is not going to fix this. I configured Varnish as described in the documentation to check if it's vulnerable, and it's indeed vulnerable. Reply from Varnish to my report was they doesn't guarantee any security when proxying WebSockets through Varnish, so shame on them. Therefore, you should consider such attacks if you are using Varnish as a reverse proxy for WebSockets. There are many reverse proxies like Nginx that are checking a response for upgrade requests they receive from the backend. For such proxies, previous attack does not work. So let's look at another scenario. We have private REST API inaccessible from outside, and now we have a public WebSocket API and a public REST API. Client invokes public API via Nginx that's used as a reverse proxy. Let's assume that exposed publicly REST API allows to check health of some website by making GET request to that external site and returning status code to the client. Malicious client wants to get access to internal API. On the first step, he makes post request to invoke public REST API, and additionally places upgrade WebSocket HTTP header to the request. Nginx observes HTTP header upgrade WebSocket and thinks that he received upgrade request from client. He doesn't check the request method or other headers, only upgrade WebSocket as an indicator. And later Nginx will transfer request to the backend. Backend will invoke public REST API and reach external resource via URL that was supplied in parameter with name U. Since the client fully controls that parameter, he can query his resource that will return 101 status code. Backend will return HTTP response with status code 101 to Nginx. And Nginx will check only the status code and will decide that backend established WebSocket connection. Afterwards, Nginx transfers this response to the client and keeps open TLS connection waiting for WebSocket frames. So we have TLS connection open between client and backend in reality. Nginx thinks it's a WebSocket connection. It does not check anything or alter data. It just passes data between client and the server. And now client can access private REST API by sending GET request to pass/internal. I created second online challenge for that scenario. Again, to solve the challenge, you need to access flag on localhost port 5000. And again, nobody solved this challenge, unfortunately. We have Nginx as reverse proxy Flask backend, and backend is serving on localhost port 5000. You see here a snippet from Nginx config. We are reverse proxying public API for pass/API/public, and WebSocket connection proxying is enabled for that pass. We have health check public REST API. To invoke it, we make post request and specify URL parameter in the body of the request. Backend reaches external resource, for example, google.com, and returns status code back to the client. And now we have everything to build final solution for the challenge. We open a TCP connection and send two HTTP requests in a row. First one is post request to invoke health check REST API, but with additional header upgrade WebSocket. As a parameter, we pass URL that we control and that returns a response with status code 101. And the second request retrieves the flag. Let's see how it works. Here is our solution script. Again, it has two requests. The first one establishes fake WebSocket connection to the backend. And the second one retrieves the flag by accessing internal API. And when we launch it, we should get the flag. Yes. But things that almost all proxies are affected by this thing. And good thing that exploitation is limited since you need some minor vulnerability on the backend. For example, external server-side request forgery. However, external SRFs are quite widespread and they are considered low severity issues and are rarely fixed. That's bad. And before wrapping up, let's drop some words about discovering WebSocket APIs during we are testing web applications. Obviously, we can monitor HTTP traffic for upgrade requests, or we can grab through JavaScript files for patterns that reveal presence of WebSocket API. And we can even try to establish WebSocket connection to each URL we observe. It sounds not sensible, but believe me, you can sometimes find hidden WebSocket APIs using this method. In conclusion, I want to share my ideas regarding further research on that topic. In my opinion, it's interesting to look into security of WebSocket subprotocols. Another interesting topic is to discover more smuggling techniques. I've demonstrated you two techniques, maybe there are more. For example, I have not yet touched how WebSocket is working over HTTP version 2. It's interesting, I think. And that's all for this talk. If we have some time for questions, I'll be happy to answer. Yes, there are some companies that pays for such bugs. I've already sent them reports. For others, no. But you sent them anyway? Yes. I'm going to make a GitHub page with describing this attack. Yes. Yes, you are right. That there is an opinion that there is no security perimeter, or everything is accessible. But in reality, there are some some products, for example, that's used for by DevOps, for example, that has some private APIs that listening on localhost, for example, and gives you some privileged access to some functionality. So yes, this is a big problem, but now I think yes, it will remain the same. Yes.
Can you give an example of the worst attack that you found?
Okay, for example, you can bypass web application firewalls with this. Completely bypass. Because web application firewalls usually do not inspect WebSocket traffic. So you can access, through this bug, you can access vulnerable endpoint and exploit vulnerability. Okay, thank you very much.